infinite sequence. So we would always have this assumption that infinite sequence of integers so a naught can be any integer, and we would have always assume that these are all positive integers. So they are at least one. All the rest. So an we don't assume anything on a0. It can be any integer, positive, negative, or even 0. But all others are strictly greater than 0, meaning they are natural numbers. They start from 1. And let xn be the continued fraction. So finite continued fractions we know. So a priori we cannot even write the notation. That we cannot write this infinite continued fraction before we address the issue of convergence. So, but we can write finite parts of it. So this is the first n plus 1 terms ending with an. So that's obviously a finite continued fraction, as we have seen earlier, with the same assumptions. So we know quite a bit about this that we are going to use. So this we can write for every n. So n can be very large. We can write it for every n, but we can't write the infinite thing before we look at the convergence. So let me recall some facts which we already know. Those just remain the same. Yeah. So these are called convergence, as we have as we called them earlier. So these are convergence, the same thing. What we know is even convergence form an increasing sequence. Yeah, so even convergence. So what do we mean by even convergence? Even convergence is even this, the index is even x to m for any natural number n. So even convergence form an increasing sequence. One second. Just increasing sequence. And odd convergence so they are of this form, that x2m plus 1 to m plus 1 form a decreasing sequence. Decreasing sequence. This we know. We also know that every even convergent is smaller than any odd convergent. So every even convergent is less than any odd convergent. Yeah, so x so x2m is less than x say 2k plus 1 for all m and k. So these are the three things we would require to start with. So therefore, just notice the first fact. So even convergence form an increasing sequence. Therefore, so x. So let's write it like this: that even convergence. So just look at the sequence formed by even convergence. Yeah, even convergence x2m. So all of them are bounded above by x1. Yeah, in fact, strictly. So all of them. So all even convergence are bounded by x1, and it's an increasing sequence. Therefore, it converges. So we use these two facts together. Even convergence are all bounded by x1. So they are bounded by any odd convergence, and we can just choose x1. Just choose a fixed one. So even if you can choose x3 or whatever you want, so that's fine. X1 is okay. So even converge, and they form an increasing sequence. Increasing sequence. So therefore, they have to converge. So therefore, they have to converge. So suppose they converge to some, say, xi1. Suppose x2m converges to xi1, some real number, as m goes to infinity. Similarly, the odd convergence are bounded below by x2. Odd convergence. So this is one fact, this is another. That odd convergence. So if we just look at the sequence with odd convergence, 2k plus 1, 2k plus 1, this is bounded by, say, sorry, bounded below. This is bounded below by x2 for all k greater than equal to greater than equal to 0. So all odd convergence are bounded by this, and they form a decreasing sequence. So decreasing sequence bounded below. Decreasing sequence. And therefore, they have to converge. And suppose x2k plus 1 converges to, so this odd convergence converge to xi2 as k goes to infinity. Since all odd convergence are bigger than all even convergence, so xi1 is definitely smaller than xi2. So clearly, xi1 is less than equal to xi2. We cannot a priori say that they are equal. They go to the same limit, but that is what we want. And we want this xi1 and xi2 to be equal. And then we say that the common value is the value of the infinite continued fraction. So that is how we define infinite continued fraction. So how do we prove that they are equal? So let's prove that. So let's write that as a claim. So now we claim that Xi1 should be equal to Xi2. So to establish this claim, we look at our previous working with finite continued fraction. So just remember that we have shown that this Pn minus Qn, by the way, so just to recall the notation, this convergence were all written as P. So nth convergence was written as Pn by Qn. This is a rational number, so Pn by Qn. And we have proved several properties of Pn and Qn. Among them, this was one of this. So the nth convergence convergent. Okay, let me write the full thing. So nth convergent minus the n minus 1th convergent. So this is minus 1 to the power. Let me write the correct power. It was n minus 1. Yeah. So this is n minus 1 by Qn plus 1. No, Qn minus 1. Qn minus 1. So whatever we already. Now, so this is what we would require. So this we have already seen. So we call this. So we call this. Now put absolute value on both sides. So Pn by Qn, Pn minus 1 by Qn minus 1, then if you just put the absolute value, then this is 1 over Qn minus 1. And this is what is our xn. This is same as xn. So xn minus 1, the absolute value of the difference is 1 over Qn minus 1. We also know that, let's recall this again. So recall this, that Qn's are all greater than equal to n, including at n equal to 1. So they are all greater than equal to n. In fact, beyond 1, they are strictly equal, but let's check just greater than equal to 1. So this fact implies that xn minus xn minus 1 is less than equal to, so we are using a lower bound for the denominator, therefore we get an upper bound for the fraction. This is n into n minus 1. Yeah, so of course we are talking about all n greater than equal to, so greater than equal to yeah, let's not take 1. So that will be a problem. Greater than at least. Yeah, so we have this. Now put n equal to 2m. So choose it to be an even number. Then x2m minus x2m minus 1 is less than equal to, so n is 2m. So this is 2m into 2m minus 1. And we know that this x2m, so this is what we have already proved, that this converges to Xi1. Yeah, we have shown that this converges and converges to Xi2. So if this converges to Xi1 and this converges to Xi2, And note that the right hand side, this converges to 0 as m. So all these are when m goes to infinity. So this right hand side goes to 0. So therefore xi1 have to be equal to xi2. So therefore xi1 is equal to xi2. So we denote this common value by x. This common value by x, and it is yeah. So and we can also use the infinite continued. We can just extend the continued fraction notation, but that's just a notation. And also write x equal to, so this is the continued fraction related to the infinite sequence we started with. So we can write it like this, but the meaning is given by whatever we discussed so far, that even convergence are converging to even convergence and odd convergence, they are all converging to the same real number, and that number is the value of the continued fraction. Yeah. So this is just the definition of continued fraction, and obviously this will remain true, that just by the convergence.
I have a doubt.
Yeah, sure.
Professor, in the earlier we have proved that xi1 is less than or equal to xi2.
Yes.
Now we have proved that they are equal.
Yeah.
Our motivation is to prove that both of them are equal.
Right.
From this statement, it means modulus of x2n minus x2m minus 1 tends to 0 itself will give the result that they are equal.
That's right. Yeah.
Then what is the necessity to prove that xi1 is less than or equal to xi2?
Oh no, it's not necessary. It's not absolutely not necessary. True. It's not necessary. It's just follows from the construction. It is not necessary.
Fine.
Yeah, you are absolutely right. It's not necessary, because we are using absolute value anyway. Yeah. So the first obvious fact is all the even convergence are going to be less than equal to x, and all the odd convergence will be bigger than x. So x2m less than equal to x less than equal to x2k plus 1 for all m and k. So all suitable m and k. So this is a fact, of course. It just easily comes from our construction. Yeah. So we should also define the complete quotient. So that's also an infinite thing. So we should define it carefully. So just like that. So for finite case, it was this thing that init quotient was this starting from a to the end of the continued fraction. That was in the finite case. We defined it with an dash. This notation was an dash. So that was the finite case. So we are going to simply take the limit. So here the definition is an dash is just the limit capital N going to infinity, capital N going to infinity, a n to a capital N. So that's the complete quotient in this case. And if you look at this a n plus 1 dash, then this is limit. So that's the definition. So this is the definition. It's defined like this. And then note that a n plus 1 is also just the same. A into, sorry, a starts from, yeah, so a n plus 1, so small n plus 1, to a capital N, and capital N goes to infinity. So we can write this. Okay, I'm just making a, yeah, I mean, just making a little bit of mistake. So this, because I should start with this a n itself. I want to just connect a n and a n plus 1. So we should start with this. Yeah, start with a n. Otherwise, I have to write a, I have to subtract things, which I don't want. So a n. So we start with a, the same thing, exactly the same. Yeah, this is not, this looks like Q actually. This is, yeah, I should write it properly. This is a n. These are not Q's. A n. Yeah, so n goes to infinity. And now let's write this as a n plus 1 over a n plus 1 to a n. Now the limit is on capital N, not on small n. So small n is just moved here. And then this should be 1 over the limit. And that's the n plus 1th complete quotient. So what we got from here is that a n dash is equal to a n plus 1 over a n plus 1 dash. And this is going to be, so all these complete quotients are greater than 1, of course, because all these sayings are greater than 1, at least 1. And therefore, this part is less than a n plus 1. And and this is positive, so this is also greater than a n plus 1. So we can conclude that a n is strictly less than a n dash. It's strictly less than a n plus 1. Therefore, as we have seen earlier, the same thing holds, that integral part of the complete quotient, nth complete quotient, is the partial quotient, an. Ans are called these partial quotients. So that relation remains exactly the same. Yeah. So we have some consequences. So the consequence in the case of finite continued fraction was uniqueness of the expansion, except for a case when you when you have when you allow 1 at the end. So we know that we can always write it in two ways if you allow the last entry to be 1. Otherwise, if the expression is unique, the same thing holds. So consequently, we have the following. Continued fraction with the same value must be identical. Identical. They have to be identical. So that's one. So we'll have same conclusions, and also note that every finite continued fraction is a rational number. So if we take an irrational number, then the continued fraction expansion has to be infinite. So every irrational number, this is also a consequence. The continued fraction algorithm for irrational number is not going to terminate, because if it terminates, then we get a rational number. Therefore, it's always it never terminates. So we can write that every rational number can be uniquely written as a simple okay, the word simple I was not writing. So simple means we have I'll just recall that. That's better. So simple infinite continued fraction. Simple. So what is simple? Simple, let me just recall, because we haven't talked about simple for quite some time. So simple continued fraction is the one where we write 1 in these numerators. So this is 1, this is a1 plus 1. So it is always 1. a2 plus, we always write 1. So that's what is simple. That's it. That is called simple continued fraction. And a non-simple continued fraction might have other integers here. They have to be integers, but there can be other integers. So there were some interesting cases of non-simple continued fractions as well. Some numbers has nicer non-simple continued fraction expansion than simple continued fraction expansion. We will talk about that maybe later, but not now. Now we just for the theory we would always concentrate on the simple continued fraction. The recurrence relation is easy in this case, so that's the reason, and it works for most in most cases. Okay. So this is just to recall what is simple. And whatever we have seen earlier about the approximation with convergence remain the same. So we should also write that as a fact. So also fact is this, just like the finite case, x minus pn by qn is less than 1 over qn plus 1. qn plus 1. And this is because qn's are increasing, so this is less than qn square. So this can be proved in the same way as in the finite case. So proof same as in the finite case. Okay, so we are done with basic facts about infinite continued fraction. Let's see an example. We actually have seen an example in the beginning itself. We in fact calculated some few convergence for yeah, I mean, I shouldn't say yeah, we actually calculated a few convergence for this square root of 7. And we have seen that. In fact, we have seen more. We actually saw that the continued fraction expression of square root of 7 is periodic. So it starts to recur after a finite stage. So we'll deal with that. We'll deal with general form of that a little later. Now it's time for an example. Let's just write an example. So this example is quite similar to what we have seen for these paper sizes. Similar example of somewhat similar spirit. Let me just put a line here. So an example. So let me see how much page I have here. Maybe I should just go to the next page because it requires some drawing again. So I like visual examples. So this is so an example of infinite continued infinite CF. Let's write CF for continued fraction. So the example is like this. So it requires some drawing. I have to draw a rectangle again. Just start here. Something like this, maybe this. Yeah. So let's look at this rectangle. So let the length and breadth has a ratio of alpha is to 1. So if this is alpha, this is 1. This is alpha, this is 1. So length is to breadth is equal to alpha is to 1. So length is alpha, breadth is 1. So that's just the ratio. Can be any unit, etc. So that's just the ratio. And now again it's a kind of a game. So we just cut the largest possible square. So at every stage we cut the largest possible square And then the remaining portion has to have the same proportion. So what we do, we cut a square. So this is the rule. So let's write it as a rule. Cut out. Okay, cut the largest square out. Largest square. So that's like step 1. Step 2 is the remaining rectangle. So obviously a rectangle remains if you cut out a square, cut out the largest possible square. The remaining rectangle must have the same ratio of sides. Ratio of length and breadth. Yeah, so let's do that. Let me just draw a line to cut this. So it should be somewhat like this, somewhat like this. So we cut the largest square. Of course, largest square is this 1 cross 1. So this is 1 cross 1. And what remains, the whole thing was alpha. This was alpha. So what remains is alpha minus 1. This is just alpha minus 1. And this is 1. And now what I want is the ratio to be the same. So we want the ratio of the length and breadth of the rectangle. So this is the size of this is 1 into alpha minus 1. That's the ratio. And that's this rectangle. So what we want is, let me write that. So length is to breadth should be alpha is to 1, which is what we started with. Alpha is to 1, and that should be same as the remaining rectangle when we cut out the square. And there the ratio is obviously 1 is to alpha minus 1. 1 is to alpha minus 1. Therefore, we have the equation that alpha by 1 is equal to 1 by alpha minus 1. So this is alpha. So alpha square minus alpha minus 1 is equal to 0. So alpha, the ratio of what we have started with should satisfy this equation. Now what can we say about this alpha? We can of course solve this equation. So if we solve the equation, then we would just use the Sridharacharya's formula, and then we would get that 1 plus square root of 5 by 2. So that's a clean solution. Of course, you don't take the minus 1 because alpha is positive. It's a ratio of the sides of a rectangle. So it's positive. So we take this this square root, positive square root. and this is 1 plus square root of 5 by 2. But that doesn't reveal much. That doesn't reveal much. So what it is? So if you just put it into a calculator, which is just a simple calculator, then it will give you 1.618. In fact, I just use my phone to do it. So this 3, 4. Yeah, I mean, of course, it's an infinite decimal. It's going to recur. But this is what it does. This is an approximation that you easily get. But this does not reveal any pattern. It just doesn't say anything more. It just gives you some haphazard numbers, lots of numbers. But it's not very revealing. So let me be precise by what I mean. Now let's try to write it in continued fraction. So CF for alpha. Writing it in continued fraction is rather easy because of the formulation of this equation. So I can write it as alpha square equal to alpha plus 1. And then divide both sides by alpha. So alpha equal to 1 plus 1 over alpha. And that's what we need. That's all we need to write the continued fraction. And then we can just simply continue this. We can just replace this alpha by this alpha. So it just goes on. So continued fraction expansion is this. So 1 plus 1 over 1 plus, so all these are going to be 1. So it's an infinite continued fraction expansion with all partial quotients to be 1. So all partial quotients are 1. So that already shows a nice pattern, but there are more to it. So by the way, so if we want to just find a rational approximation, so it's so easy to find rational approximation now. Just by hand. So if you just take 5 5s, which I just did, so this is what would give you 8 by 5, which is 1.6. So without even using a calculator or anything, you can approximate it to the first decimal. So it's so trivial to find the rational approximation. Whereas if I just give you this number 1 plus square root of 5 by 2 and ask you to find a rational approximation, that's quite difficult. I mean that you don't see any easy way of doing it without this help of the continued fraction. But continued fraction expansion, in fact, the expansion is so easy to write, and then you immediately get rational approximation to the degree you want. I mean, this is just 5. I just took a random 5 because I can just do it quickly by hand. So if you just use something better or spend some more time, then you can get much better approximations. And as we know, the convergence also converge quite fast. We know the rate. So continued fraction expansion is really a nice way of writing rationals, because you immediately get a rational approximation. You immediately know the size. There is a little more to it, more to this particular number. Let's see that. So just enough to look at the continued fraction expansion. And let's just recall. So just recall this, that so we want to look at what this sequence of Pn's and Qn's are, the denominator and the numerator of the convergence. So P0 is A0, which is 1. P1, okay, let's write P0, Q0. Q0 is always 1. And Q1 is A1, so which is also 1. And P1 is A0, A1 plus 1, therefore it is 2. Now what is Pn? Pn is An Pn minus 1 plus Pn minus 2 for all n greater than equal to. That was the relation we have seen earlier. And what is it here? Because all ans are 1, so this is Pn is simply it's just a side. So Pn is simply Pn minus 1 plus Pn minus 2. And what about the Qs? So Q1 and Qn, again the same thing. So Qn is An Qn minus 1 plus Qn minus 2 for all n greater than equal to 2. And therefore, because all ans are 1, so we get Qn minus 1 plus Qn minus 2. So let's write down a few convergence. Yeah, let's write down a few convergence. So convergence. So if you notice that you are actually having Fibonacci sequence for the denominator and numerator both. Because the nth term is the sum of the previous two terms in both cases. So they are all elements of all integers in Fibonacci sequence. So convergence, let me write the convergence. So 2, 3 by 2. So these are successive convergence that I just calculated. You can use this online calculator to do a lot of this. 3 by 5, 8 by 5, and yeah, actually you just add it, write it in the numerator, and the denominator is the previous numerator. So that is how it just goes. Okay. No, sorry. You have to add the numerator. Sorry, I just. So 13 plus 8, 13 plus 8. Sorry. So 13 plus 8 and also. So 13 plus 8 is 21, and this remains 13. So whatever numerator you have, you just bring it to the denominator and add numerator denominator to write the numerator. So this is what? 34. So it goes on like that. So these are Fibonacci quotients. So all these numbers are Fibonacci numbers. The number alpha is actually called golden ratio. So there is a lot of literature on this. Yeah, so this is also called golden ratio. I should just mention that. Maybe you already know. Yeah, so this is not just an example. So what we have seen is that given an irrational number, it's very easy to figure out the mm, rational approximation if we write it in continued fraction expansion. And continued fraction expansion in this case revealed some pattern, some inner pattern that this is actually connected to Fibonacci sequence. Okay. Yeah. So for examples. Okay. Yeah. So I actually want to talk about another small example. Okay. Let me do that. So another small example, which is very much at hand all the time. We don't notice it often. So that's but it's an example of a it's a rational number. So it is uh, it's a finite quantity. So it has to do with calendar. So another example. So another example. So this has to do with calendars. So we primarily have two kinds of astronomical calendar. One is, so these are these astronomical calendars. So that they are calculated depending on some celestial movements. So calendars themselves are not examples. So just starting there. So astronomical calendars. So essentially, yeah, I mean, I shouldn't say essentially. They are generally used. We generally use two types of astronomical calendar. One is the solar calendar. Solar calendar. So today is 15th February in solar calendar. So that's a solar calendar. It's the usual calendar that we always use. The English calendar is Gregorian calendar. Gregorian. So that is an example of solar calendar. There are others, but they would be very similar. And two is lunar calendar. So an example of a purely lunar calendar is the Islamic calendar. So Islamic calendar is purely lunar. But there is a third type of calendar, which is called lunar solar calendar. So it keeps track of the sun as well as the moon. So sun is to keep track of the season, and moon is essentially for various religious purposes, for some celebrations, etc. And so that's called the lunar solar calendar. So I would write that. So that's a kind of a combination of these two. So lunar solar calendar is generally called lunar. Lunar solar calendar. So an example is Hindu calendar. Usually, whatever is followed for festivals, etc., is a lunar solar calendar. So this lunar solar calendar is very interesting. because it's trying to take account of these two different periods, there is something interesting arises. So I talk about that. So let's look at this. So a solar year. So what is a solar year? So solar year has 365 points. So there is a fraction. I should write it properly. 365.45 24, sorry, 0.24 24 solar days. Solar days. And a lunar month is 29.53 solar days. So we are trying to bring these two to the same unit. So looking at solar days. So 365.24 days is a solar year, and a lunar month is 29.53 solar days. Then how many lunar months we have in a solar year? So in a solar year, so therefore, in a solar year, we have 365.24 by 29.53 lunar months. So this many lunar months, because this is the numerator is the number of solar days in a solar year. We are dividing it by the length of a lunar month in terms of solar days, the same unit. So this quotient represents the number of lunar months. So we have this many lunar months in a solar year. So notice that this is more than 12. So if you calculate, I did that. So 12.36 12.36. Okay, this is the precise value. 3684 3876. I hope this is correct. 3876. Yeah, this is the value. Now the point is what even if we know this value precisely, it doesn't help us in bridging the gap between these two, to adjusting. So what should we do about this? And here comes the continued fraction. So what is done is to look at the continued fraction. So CF of continued fraction was known to ancient mathematicians actually. So so very early Indian mathematicians used continued fractions. So this was, there are clear evidences of continued fractions, use of continued fractions. 5, 3. Yeah. Oh, somebody has animated. So please remove. Yeah, thank you. Thank you. Yeah, I should actually stop because this is not an intentional animation. Let me just. Yeah, I forgot to do that. So disable annotation so that you don't do it by mistake. So, yeah, so let's look at the CF. So being a rational number, we have a expansion. So first has to be 12 because the integral part is 12 anyway. First entry is 12. We write it correctly. So 2, 1, 2, 1, 2, 2. So very nice so far. But then there is a huge partial quotient, 155. 155. So these are the partial quotients. So 12, 2, 1, 2, 2, and then 155, a very large partial quotient. So in this kind of situation, whenever you see an expansion, continued fraction expansion with a very large partial quotient, you can truncate it to the previous partial quotient. That will give you a good approximation because the next part, there is a jump. So the next part becomes much smaller. So that gives you a good approximation. So therefore, of course, good is a vague word. So what I mean is that it's better than better than truncating it at 2 in this case rather than in the case when you have another 2. So that will give a poorer approximation. So if we just truncate it 12, 2, 1, 2, 2. So if you just truncate it, is a good approximation. Now, if you look at this, it just can be calculated by hand. So 2, 1, 2, 2. This turns out to be 12 by 7 over 19. 7 over 19. So we have, this is exactly the number of lunar months in a solar year. So you have 12 lunar months plus an extra. Extra is 7 over 19. So to calibrate this, what is done is that every 19 year, you have to have 7 extra months. So every 19 year, so as a consequence of this, every 19 years, we have 7 extra lunar months. Lunar months. So these months are distributed in the calendar according to some religious priorities. And these special months are called what is it? This extra months. There is a name for it. Oh yeah, so it's called Adhika Masam. So these are called Adhika Masa. They are added to this calendar every 2-3 years. So there's a way to add it, so that you have 7 extra months. So if you follow Hindu practices, then they are sort of not auspicious. They have declared it to be not auspicious, etc. So whatever, that's the culture. But this is the mathematics, that you have to have 7 extra months in 19 years. So every 19 years, you need to put 7 extra months. And why is that? Because of this reason, and that is a good approximation. It's not exactly covers the entire solar year, but it's very close. And because more because of the fact that the next partial quotient is 155. So truncating just before that gives a good approximation. So that's a very interesting use of continued fraction, which is probably done very long time back, and it's in use. So that's an example. It's just it's a as mathematical example. It's very simple, but interesting in practices. Okay. So with that, we have done these 2 examples. Okay, so the next we have to move to the periodic continued fraction. Okay. I'll probably talk about periodic continued fraction next time, because I don't have much time. Let's okay. Let me just okay. Let me just define what is a periodic continued fraction, and then we can stop. So by the way, about this calendar, there is a very nice site, very nice web page maintained by NASA, which gives this kind of details, but they don't really mention this exactly this continued fraction. They don't write it in terms of this continued fraction. So if you look up Wikipedia, if you look up Hindu calendar in Wikipedia, you will see that this thing is mentioned, that every 19 years, the 7 extra months Odhika Masha is added, but they don't write down the content. They don't talk about the content fraction. So this is what goes behind it. Okay. So I'll send that link to the page on WhatsApp. Yeah, so this is what to come up next is the periodic continued fraction. So we in fact started the lectures, the first lecture itself, we saw an example, square root of 7. Periodic continued fraction. So this is what is going to be our next topic. So what is a periodic continued fraction? So if we would see it in detail next time, but just to begin, so if this kind of thing happen, that partial quotients become periodic. Oh, let me write this like this. That if there exists a k such that AL is equal to AL plus K for all L beyond some stage, let's say some capital L. So we allow some finitely many partial quotients to be random, not following any periodicity, but it should become periodic eventually. After a finite stage, it becomes periodic, so it repeats. So that's what is our periodic continued fraction. So they're eventually periodic. And how we write them? We already know. So they are written as A0, A1, up to this L minus 1, then AL sorry, AL to AL plus K. No, L plus K is going to repeat, L plus K minus 1, and these block is going to repeat. So L plus K is going to be same as L. So again, the block repeats. So this is a K length block which is going to repeat infinitely. So that's what is periodic continued fraction. We will see that these periodic continued fractions are what is called surds. So they are the surds are all periodic continued fractions. So surds are periodic continued fraction, and every periodic continued fraction is a surd. So it's a solution of a quadratic equation with integer coefficient. So we prove that, at least one part of it. We prove that next time. Okay, so let me stop here. So any questions? Anything at all that you would like to ask?
Participants, please ask if any questions.
Maybe we should stop recording when the lecture ends so that people feel a little more free to ask